I'm Matt Pleil. I'm from the University of New Mexico. Okay, and I run the Support Center for Microsystems Education, which is an NSF-funded advanced technological education center. And I've been doing this kind of work with NSF since 2004. So, it's been a lot of fun, and they keep giving me money, so I must be doing something right. I also run the MINTI-SIG group, which is the Micro Nanotech Education Special Interest Group. Students are welcome to come to those meetings and participate. We have a lot of working groups that you might be able to get something from and also contribute to. Jared just got his Micro Nanotech Education Center grant. So now I work partly for him as well, and it's great. It's a great opportunity, and it's really good for the students. That's what it's all about. It's all about the students. And yeah, so that's about it for the title slide. So let's move on to the more fun stuff. I'll be talking about applications of MEMS and specific devices, and also some systems, and then current trends. Where are things going, and how does the future look for jobs and things like that. All right, so Microsystems stands for Microelectromechanical Systems, and traditionally they were mechanical systems on a very small scale. So the image you see on the right is the world's smallest chain that one of my students, technician students, actually designed back in 2006. So Paul Tafoya made this and designed this chain using the Sandia National Labs software. And we won the design competition that year, and they actually fabricated the parts. So this chain actually works. So you can see it there, scanning electron microscope pictures, and each chain link is about 10 microns long, and it's multi-layered, and it has moving parts and all of that. So Sandia did a great job taking what Berkeley had done and expanding it and making what they call the Summit 5 process, which is basically using semiconductor technology to build these parts. Okay, so that's a mechanical systems, very mechanical oriented. And they did this in the mid-90s. So you guys hear the word nano all the time from Dr. Ashcroft, and you can see, that's on the 100 nanometer scale and smaller. Typically, what I work in is more in the 100 nanometers to 100 micron range, and that's called microsystems. So on the left is macro, you guys know about that, and in the middle is the micro world, and on the right is the micro world with a little bit of nano on there. So you can see the gear teeth, and that's similar to the gear teeth in the previous slide. Each one of those gear teeth is about 8 microns, and 8 microns is a little bit smaller than the size of a red blood cell. So if you put a red blood cell on here, it would drape over the gear teeth. So that's what's kind of remarkable of making these very small mechanical systems on a very small scale. Okay, let me go to the next one. So there's all kinds of different MEMS devices. Of course, there's the traditional inertial sensors. Inertial sensors and pressure sensors were the first two classes of MEMS devices developed back in I think starting in the late 60s a little bit, and then it started taking off in the 80s. And in the 90s, they were making inertial sensors pretty regularly. The first inertial sensor commercially available was from Analog Devices, I believe in the late 80s, and it was designed for crash bag sensing. So, a sensor needed in the car industry to detect when something crashes. And that's a case where the government said, thou shalt put airbags in cars. They came up with some sensors early on that were very simple, basically a ball of mercury in a glass tube. And if you put on your brakes hard enough, the ball will roll up the tube, create a contact between two contact points, and cause an explosion inside of an airbag. Those didn't always work the way they wanted them to. And so, Analog Devices came up with a microelectromechanical system that senses a change in inertia, which is acceleration, which is basically a force. Microfluidics are a big deal now. You know, we have lab on a chip systems. So part of those laboratory things on a chip require microfluidic channels and chambers for mixing very small amounts of material. This is really good because you don't need a lot of chemicals to do your testing, and you don't need to draw a big vial of blood or, you know, take a large urine sample. You can take very, very small samples and analyze them. So for biomedical applications, microfluidics is great. And they're also used for things like inkjet printers. In the BioMEMS realm, you know, we have lots of different applications. One of them shown here is a pacemaker. And now the pacemakers are very sophisticated. They have inertial sensors built in, oxygen sensors built in. So the pacemaker will change the pace of the heartbeat depending on how much activity you're doing. So it knows when you're going up the stairs, you know, because you're moving more. It'll speed up the heart. It'll check the oxygen level in your blood and promote your heart rate to go faster. So the old pressures or the old pacemakers didn't do that. And, you know, you'd get winded if you go up the stairs. So people with pacemakers would go up 3 stairs, wait, go up 3 stairs, wait, because the heart rate was always the same. And micro-optics is also a really cool field. I like teaching about this because it's neat. And you guys are all familiar with it if you've gone to movie theaters, maybe not for a while, but they all are digital now, and they're based on these digital mirror devices. Okay, so where do we find MEMS? Well, like I alluded to, you find them in a lot of consumer products and automotive applications. In fact, the automotive industry has driven a lot of the MEMS technology over the years and the research. Now we have smartphones. Smartphones have a ton of different gadgets in them, different sensors, and we'll talk a little bit more about those in a bit. Then we have the Internet of Things. So we have billions of sensors all throughout our life and in our environment. And now those sensors are being connected to the internet. So some of you may have, you know, sensors in your home, thermostats and whatnot that are Wi-Fi enabled, so you can change the temperature of your house from work if you want to. You can check on security systems over the internet, which includes sensors and video images and whatnot. So you also have biomedical and biochemical sensing actuation systems. So we're doing microsurgery, chemical and drug delivery, subcutaneous types of therapeutics, and then, like I mentioned earlier, the point of care lab on a chip. On the right side, you can see one of the typical smartwatches you can get now and to track your health. I actually have one. It's a Garmin. It can sense my oxygen and pulse rate all day and night. It knows my motion, of course, because it has inertial sensors built into it. And I can also check my text messages and control my my headphones, my wireless headphones, and adjust the sound. And it also has GPS built into it. So it's quite a remarkable gadget, and it's all made possible because of MEMS and microfabrication and semiconductor technology. What I really like to talk about are the smartphones, right? In the old days, they just had a few things in it that were MEMS related, maybe an inertial sensor, a microphone, and that kind of thing. But now they're adding all sorts of stuff, which is so cool. You've got 6-axis inertial sensing units. So not only does it know X, Y, and Z motion, but also roll, pitch, and yaw, right? So, and now they have magnetic sensors in your phone. You can use it as a compass. You can also use it with certain apps to look for current in the wall because it creates a magnetic field. And that sort of stuff. Pressure sensors are included now in phones. which is really interesting. There's not a lot of applications for pressure sensors, but it helps you determine altitude. So I think the application that they're looking at is navigation within buildings, because GPS signals get scrambled sometimes when you're inside of a building. So having an inertial sensor system coupled with a barometric pressure unit, you not only know how you've moved in the building, so you can track XY motion, but you can also track what floor you're at by the change in the pressure. And then there are bulk acoustic wave filters and duplexers. Speakers, of course, are now microsystem arrays. And recently they've added projection systems and FLIR cameras within the phone. So on the right upper corner there, you see one of the, I think it's a Max 1 that comes with a FLIR camera built in. You can buy another one that has the projection system in it. And what you see below is a Moto, I think a Motorola cell phone that has a projection system built in. So that's pretty cool. And the most recent one coming out in the middle of the summer is just incredible. All right, I like to use information from Yole Development Group. It's a French company, and what they do is they study electronics and microsystems and high-tech technology and where it's going into the future. And they drill down into the, what's inside the little black box, right? So here you see a slide with sensors in smartphones. Right, so there's lots of little subgroups of sensing systems. These are in smartphones. You have accelerometers and gyroscopes, magnetic sensors, gas sensors now. Bosch is coming out with gas sensors. So your phone will tell you if it's a healthy environment you're in, right? So it looks at hydrocarbons in the air. It looks at other things. And then it might say, well, you're not in a very healthy environment, so you may not want to stay in there. And then, of course, pressure sensors, humidity sensors, temperature sensors, all of those sorts of things. And then, of course, it's the data and the coding that drives the technology, right? So you have to be able to do something with that information and make decisions based on it. That information, of course, turns into data. A lot of the data is put on the internet. Right. So now you need, more servers, you need more capability, Wi-Fi capability, more bandwidth. So this is driving, again, another set of technologies. So as you can see, everything related with microsystems, MEMS, smart technologies, all of those are driving the hardware, software development, and which means tons of jobs, right? Lots and lots of jobs. So if you look at your average smartphone these days, you can see there's a ton of MEMS sensors in there. You've got, of course, the microphone. Then there are different types of microphones. Sometimes they use multiple microphones. I think one of the iPhones has 4 or 5 microphones in it. And you'd say, well, why do you need 4 or 5 microphones? Well, what it does is it puts those microphones in different places on the iPhone. And that way, when you're talking on the phone, it can do noise canceling. So your voice sounds much clearer to the person you're talking to, right? And also if you're doing video stuff on your iPhone, you can get more of a dynamic range for your sound quality. So you can kind of know what's on the left and what's on the right. So when you create a movie with your iPhone, it almost sounds like surround sound. CIS is a CMOS a camera, basically. It's based on semiconductor processing. But now you have front and rear cameras, multiple cameras, 3D cameras, and whatnot. And you can see some of the new Samsung phones coming out have like 4 different cameras on one side and a really good camera for doing selfies and Zoom meetings and stuff. Infrared imaging, multispectral imaging, laser ranger finder. So everything's in focus. So if when you take a picture, it knows how far something is. It uses a laser ranger finder. And then of course that's coupled with autofocus systems, which are moving parts. So it used to be the lens was stable, it didn't move, but now the lenses can move and do autofocus. And then parts of that are piezo transducers, which means that I put an electric field on a crystal and it changes its shape. So you can move things up and down. Particle and gas sensors, temperature, humidity, pressure sensors, and we talked about these other things. But then you have things with the communication. So you have tunable antennas. So the antennas have moving parts to them, which is kind of interesting. You have MEMS oscillators, and an oscillator can be made to run at different frequencies, and that's done mechanically. So fingerprint sensors, right? That's another MEMS device. So you can see all of this stuff is in the phone. It's kind of amazing. And now they're putting multiple sensors in one package. So Bosch is a leader in MEMS sensing technology. They started with the cars back in the day, putting pressure sensors in cars and being able to control fuel efficiency better and that sort of thing. And they've grown that technology. And of course, they want to get into the consumer markets and the phones in your house and your to be able to control your environment better. So this is one of their latest combos, and it does not only pressure, right? It's combined temperature sensing, and then humidity and gas. So it's looking for some volatile gases as well, and that's all in one package. Okay, so here's another example, and Yole goes in and actually takes products and rips them apart and to see what's inside and figure out about how much it really costs to make these things, right? So this is an interesting slide because it tells you, the package itself is about 16 cents. The ASIC accelerometer costs about 10 cents, right? And then you've got the other MEMS accelerometers are around 6 cents each. And that's remarkable because I remember just a few years ago, they were $9 just for the accelerometer. So there's a lot of price pressure to keep these things cheaper, make them cheaper and cheaper and cheaper, because you want a phone that can do everything but doesn't cost you anything, right? So it's really driven the prices down. Which is a good thing because now we're going to have medical sensors and things like that and that are cheap. So the cost of diagnosing people's diseases and whatnot has greatly decreased in price. And you can ask some of the biomems folks, PCR where they do the DNA work now is getting smaller and smaller and smaller and cheaper to do. It used to cost $1 billion to sequence a human, and now it costs $100. Yeah, this is great. I want you folks with the cell phones to go find this app. It should be, I think it's also for Apple, but I know it's definitely for Android phones. It's called Sensor Kinetics. Okay, and what's really cool about Sensor Kinetics is it's an app that taps into all of the sensors in your phone. So I really like talking about phones and the sensors in the phones because everybody carries around a bunch of sensors. Now you can use Sensor Kinetics to do your experiments in your labs. All right, so you can tape it onto something that's moving, and you can get the motion of that device, that thing that you're trying to look at. You can use it for magnetic fields. You can use it for all sorts of stuff. So the phones are great, has lots of sensors, and then you can actually see what the values are coming out of the sensors, right? And that's what allows you to be able to, like, when you're playing a game on the phone, you tilt it and you can move things around and whatnot. Those sensors allow you to be able to do that when it's coupled with the right software. So I really like this this graphic here on the right. It shows a change in air pressure. And I did this last night. I took my phone and I put it on the desk and I tracked the pressure. and then I put it on the floor and tracked the pressure. Okay, and then I zoomed in on that trace and I could determine the difference in pressure from being on my desk to being on the floor. And then I looked up on the internet, you know, how many millibar, you know, is equal, a change in air pressure is equal to about 1,000 feet. And you can Google that. And it's about 31 millibar, and it changes a little bit. You guys are at sea level, so, you know, it might be a different number. But I looked at 5,000 to 6,000 feet. I'm at about a mile up. So, you know, you look at the millibars and you zoom in on the graph and you see, oh, I've got two different pressures. So I did a little math. I said, oh, it's 0.075 millibar difference. And then I determined, you know, well, if 31 millibar is 1,000 feet, what's 0.075 millibar? And you can check my math. And the math came out to being 2.4 feet. I got my tape measure and measured it. It's about 30 inches, which is 2.5 feet, right? So that's really neat, right? So you can use the air pressure difference to determine the height difference of where you're at. So you can do this kind of stuff, you know, whenever you climb, right? When I go hiking and stuff, my phone knows how much altitude I've walked, right? And it does that mostly, I think, from GPS, but it can also do it from the pressure difference. So this is really cool stuff. Okay, and you can see I'm at 850 millibars or so in Albuquerque, and when you guys check it on your phone, you're going to be about 1,000 feet because you're right at sea level. So you can actually see the difference in the pressure, and you can do the calculation and see what altitude I'm at. All right. So accelerometers, we talk about those a lot because that's one of the older applications that they came up with back in the day. It's accelerometers is a meter that measures acceleration. What it really does is it measures force, right? Because F equals ma. So they also call them inertial sensors. So it measures a change in inertia. And inertia is m times v. Okay, so a change in inertia is a change in velocity, right? Because usually you don't lose mass unless you're in a spaceship. So an inertial sensor will sense a change in velocity, which is again an acceleration, which is an accelerometer. So that's how all of these terms interact. So I use inertial sensors interchangeably with the term accelerometers. They're basically the same thing. So in pacemakers, you know, they have accelerometers in there, as I mentioned before. They also put them in gaming systems, right? Because when you move either your controller or your phone now, things change on the screen. So you need a way of measuring that change, right? And then airbag deployment. Now we don't just have front airbags, we got the ones from the side, right? The ones from the ceiling even. So, you know, if the car hits something, your airbag in the front goes off, then a car coming across the side hits you on the side, then the side airbags go off. Then a car hits you on the other side, the other airbag goes off, and maybe your car rolls and then the ceiling airbags go off. So they're all different sensors measuring different directions. Okay, and computer stabilization, of course, camera stabilization. We're all familiar with that with our cell phones. If you look at the old cell phones, if you moved a little bit, your picture was really blurry. Now you can be moving around and doing all kinds of stuff and your picture looks good. GoPros, great example of image stabilization. Yeah, so anyway, you get the idea. There's lots of applications for accelerometers, but the question is how do they work? How do they measure that change? Well, on the left and right there is a picture of the same thing. This is an analog device inertial sensor I got years ago from a buddy of mine who got a whole roll of these inertial sensors from analog devices. for educational purposes. So we deprocessed a few of them, and then we took some pictures of them. We wanted to see what's inside the little chip. And you can see it's a cantilever right here, right? I hope you can see my mouse. So on the left side, you see a cantilever beam, and it's a little bit bigger on the end, and that's what we call a proof mass. So you have to have some kind of mass that will respond to a change in velocity, right? F equals ma. So you need an m, right? So if you can imagine, if I take that chip and I move it really fast, this cantilever is going to want to move in response to that. It'll bend. So it'll bend and it'll get closer to the chip or further away. And you can measure that electrically through a capacitance sensing system. So now I can measure a change in an electrical signal that's based on the amount of distance that cantilever moved, right? And once I can do that, then I can get a voltage. And once I have a voltage, I can amplify it, I can condition it, I can do things with a voltage. And then I can take that information and make a decision on it. So you can input the voltage into a logic circuit, and then the logic circuit can decide, is that change big enough for me to send a signal and explode the airbag? Okay, so this is what it looks like inside the chip, and this is an old chip. So I've got a couple hundred of these. If you guys are into electronics, you know, I can send you half a dozen. And then there's a spec sheet for it, so you know how to hook it up with your breadboard, and you can actually tap into the signals coming out of it and then move it around and create your own sensing system. And then there, you know, that was an out of plane one where the cantilever moves, but you can also imagine moving things with interdigitated comb drives, right? So you have interdigitated combs, and as these things move back and forth, they're going to change capacitances, right? And again, now you get a change in an electrical signal. You can do something with it and make a decision. So you can see how these things move around. Okay, and so that's what those look like. So in the Wii controllers, they have both kinds. They have in-plane and out-of-plane sensors. So it's a 3-axis accelerometer in the old Wii games, and now they're in everything. And this is what it looks like under a scanning electron microscope. And so you can see, you know, what these chips look like. So you got XYZ or XY measurements here. And then here you have a Z measurement, which is out of plane. Okay. And you can take all that data, crunch it, condition it, and do something with it. You can not only sense things with these interdigitated combs, but you can also move things. So if you put a voltage on one and put an opposite voltage on the other, they're going to want to attract and get closer. If you put the same voltage on both, they're going to want to come apart. So you can get some relative motion going, right? So that's what we're seeing here. These are interdigitated comb drives, and you can actually move things back and forth. And, you know, if you want to bring it back to where it started, you need a spring. So that's why we have springs in here. And this is based on the Sandia surface micromachining process. The same process used to make the flip mirror on the bottom right here. So they can move two pieces, they pop up, and you can make a pop-up mirror. And you could think of 100 other things what to do with this. We've got inertial systems in cars, and we already mentioned that, but this shows you everywhere where you see these kind of sensors. Okay, so lots of sensors in a car. They keep adding more. Pressure sensors, another class of sensing. That little gray box you see here is from Lucas Nova sensor. This was back in the 70s, I think. It went on the end of a catheter, and they could put the catheter up inside of you, right, and measure the blood pressure. So they could actually take it, put it close to your heart, or maybe inside the ventricle of your heart, and measure the blood pressure inside your heart. And these things were made back, I think, 70s and 80s. It's an intracardial catheter tip sensor. You see 3 of these sensors on the head of a pin. Whoops. Okay. And that's what's going on there. Big thing, putting in air sensors inside of tires so you know when to put air in your tires. Most of you have more modern cars than I do, and you may have that already in your car. And some cars, it tells you what each tire pressure is and when you have to fill up the tire. And that's all done with MEMS devices and an RF transmitter that's all put inside of the car tire. Okay, you also have barometric pressure sensors that you use, to measure the air pressure. Can be used in HVAC systems in buildings and whatnot. And then again, biomedical applications. Okay. A lot of the sensors are based on cantilevers. I have a nice cantilever kit I sent Dr. Ashcroft. So you guys can play with that. And a cantilever is just a stick that's held in place on one end. So you don't have to use what's in the box. You can do anything you want and do experiments on that and learn all about resonant frequencies and how you can change the natural resonant frequency of a cantilever and how they're applied to different applications. Yeah, we use cantilever-based sensors for biomedical applications, pH sensors, therapeutic systems, of course, atomic force microscopes, which I think Dr. Ashcroft talks a lot about in your classes. How do you measure an atom? You use an atomic force microscope. Well, that's based on a cantilever, a MEMS device. Read-write storage devices. There's a really cool one that IBM came out with a few years ago. It's called the Millipede, and I have information on that. Environmental monitoring, of course, food production and safety, RF switching. So that's more of an, not a sensor, but an actuator. And then various probes, of course, are cantilever based. So here's a micro actuated switch. So in the middle, you have an electrode. You put opposite voltage on it, it tends to pull it down. And then the end comes down on some contacts, which are slightly higher than the electrodes. And you can connect 2 things together and turn something on a very, very tiny scale, okay? If you take a cantilever and you coat it with something that other things stick to, right, preferentially stick to, when you add that material onto the cantilever, it's adding mass to it. Well, when you add mass to a cantilever, it shifts its resonant frequency. You can measure this shift in resonant frequency with electronics. Now you've made yourself a sensor. Okay, very simple principles. A little tough to build a whole system, but this is becoming more and more commonplace now. This is what a cantilever array might look like. This is from a university where they've made an array of cantilever beams, so they can coat each one with a different material, and you basically make an electronic nose. Okay, and there's a nice laundry list of different applications that are based on cantilevers. And the reason we can do this is because we use nanotechnology to enable the functionality of these sensors. So you put a small coating on there. So you can put antibodies on there, and then if the right virus comes by, it'll stick to the cantilever. Now you've detected that virus. That would be one bio application. You can also do complementary molecules. And you can measure very, very small amounts of mass. So the Craighead group in Cornell, they were able to measure down to the attogram. So, we talk about nano, 10 to the minus 9th, and pico, right, 10 to the minus 12th, and then femto, 10 to the minus 15th. Atto, I think, is 10 to the minus 18th. And Jared, you can correct me if I'm wrong, but that's a really small number. And if you measure 1 attogram, how many molecules is that of gold, or how many atoms of gold is that? Okay, it's not a lot. And then here again, chemical sensor arrays, right? We mentioned that already. You coat it with different coatings, and then different target molecules will stick to the different coatings you have. Okay, and there's two ways to do it. You can measure the resonant frequency shift, or if the coating changes its stress, you can bend it. So you can bend the cantilever, and then you can sense how much it bends, and you can do that electrically, or you can reflect light off of it, and if the direction of the light shifts, you know how much it bends. So lots of cool things you can do. And again, here's your atomic force microscope. These cantilevers can be anywhere from 2 to 20 microns. That should be microns, not millimeters. Microns wide. And then at the end, you've fabricated a very sharp tip. And that tip goes across the surface. It doesn't touch it. But what you're looking for is when you get close and that tip gets close to the surface, it actually can conduct electricity. So at a certain point. And then when it's further away, it doesn't conduct. So you have a feedback loop. So you try to keep that tip right just a certain amount of distance above the surface. And then as you move the surface along and you come to an atom, right, the tip has to go up and then it comes back down again. And you measure that motion of the tip, and that gives you an indication what the surface looks like. Okay. And then here again is a cantilever with, I think that's 6 attograms at the end of the cantilever. It's a little gold dot. And this is was done by the Craighead group probably 20 years ago now. So 10 to 20 years ago. And you know, it just shows you what you can do with cantilevers. And you can do it static or dynamic mode. Okay. So I'd like to teach about cantilevers. You can learn a lot of different things using cantilevers. I can teach you calculus using a stick, and not just to hit you with it, right? You can learn about different materials and their response to stresses and forces. So you can get the bulk modulus of a material by looking at its mechanical properties and all that. And then, you know, if you want to make these things, you can learn how to do this in the clean room. So we actually do have a cantilever, a bimorph cantilever design, and you can see part of the design in the upper right corner there. And then in the middle bottom, you can see the actual cantilever printed out on a wafer. So if you come to UNM in the summer, you know, you can either make our pressure sensor, or you can try to make some bimorph cantilever beams. Okay, MEMS sensors are based on biomimicry. So a lot of the nanotechnology we've learned about comes from looking at nature. So how do geckos walk on glass, right? It basically goes all the way down to the van der Waals forces. The geckos can get their pads, the little pointy things on their pads, so close to the glass that there's a strong attraction that occurs because it's so close to that other surface. So, you know, we learn from nature, and we also try to emulate nature. And that's what this graphic is trying to show. So we can smell things now electronically with MEMS devices. We can see electronically. We can sense motion. For example, your ear has a 3-axis accelerometer built into it based on fluid dynamics. And the little cilia, I think cilia, inside the canal, right? It moves when the fluid in your canal moves, and that helps you determine which way is up. And people that have vertigo, that liquid inside their ear canals starts to get gummed up, or the cilia doesn't move anymore, it gets stiff. So now you can replace that with a MEMS device. And your brain actually learns to decode the signals from the inertial sensor. So they've been successful in reducing vertigo for people with those severe issues. So, you know, we're becoming cyborgs in a sense. And you have pressure sensors and humidity sensors and all of that. And, you know, people have those kind of sensors. Let's see, here's some mega trends on sensors and actuator markets. So you can see there's a lot of money in this. Okay, so again, we've got sensors and actuators, and two types of MEMS devices. Okay, and then we've got things like subgroups of that. One is microfluidics. So that means small in fluids, right? So you got inkjet printers, right? Those are the first MEMS microfluidic devices. You could print, very tiny droplets, picoliters at a time from an inkjet print head and to make pictures. Now they, of course, use inkjet technology to do 3D printing of very fine structures using different materials. You can do almost nano level printing using this type of technology. So there's a lot of research being done on how we can leverage inkjet printheads to do other things. We have micropumps. Those are real useful for diabetes therapeutic systems. So you want to pump just a little bit of insulin, you need a little bitty pump. And if you want to put it under the skin, the smaller the better. So you can see there's a micropump for insulin on the left there on the tip of someone's finger, and then there's a close-up of it on the right. Okay. This is a really cool device. This is built at Berkeley, and the idea is you can run an experiment. So you might have a 10 by 10 array of little wells on a very small space. And then with a microscope, you can see how each of those little cells are working. So if you put a reaction in there, you put viruses in there, or you put cells, and you treat each one differently with the microfluidics coming in, maybe you'll have a pH array across all of those different cells, or you add, I don't know, some kind of mRNA things in there, whatever the case may be. You can do an experiment, 100 experiments at one time, right? So that's kind of the idea there. BioMEMS applications, again, pressure sensors, we talked about that, but also things like microgrippers. So the little tips on the end of the, what do they call that? There's a surgical tool, a robotic surgical tool. I think it's a Da Vinci. And, the doctor looks at a screen through like a headset, and then he puts his arms into these haptic devices so he can feel response from the robot. But at the end of the robot, there are things that are so tiny, really tiny instruments. So when he moves his hands an inch, right, it might only move a micron or two in real life, right? So it's like a pentagram in that sense. So he can move things around like this because we're only good to, tenths of an inch or hundredths of an inch, maybe in our motion. But if you scale that down, you can do extremely fine things like, repair capillaries and things like that. So that's all done through electronics and robotics. And then right at the end, you have very fine sensors and actuators, so you can move things very small amounts. Okay, and then you have things like tactile sensor arrays at the end of those devices that are used for microsurgery. But you can also make drug delivery systems based on microneedle array. So you can make an array of needles and then coat them with whatever drug you want to put, in a person. And then you just put the array on your arm like a patch. So a lot of the patches have a very fine array on them. And you need a little bit to get past the first few layers of skin so you can deliver the drug to an area of the skin that actually can do something with it. And since they're microneedles, you don't feel them. Okay. And my favorite is the artificial retina. So this was started, I think, as a project at the national labs, but I think a few companies have taken it over. And they're making little artificial retinas for people who have macular degeneration of their retinas. They replace it with the synthetic retina. It produces electrical signals based on light that's hitting it. and then they interface it with the optical nerve. So they get the optical nerve to respond to those little electrical pulses. The optical nerve sends a signal to the brain, and after a while, the brain knows how to decode it and create an image, right? It's just like babies when they first open their eyes. They don't know what, they're getting all kinds of data flooded into their brain, and they don't know what it means. So the brain has to learn to decode all of that and create images. Okay, so it's like artificial intelligence. They're trying to teach computers how to see. People do that naturally. And you know, if something breaks and you replace it with something else, the brain figures it out on its own. Okay. Microneedles, right? Some more microneedles here. These are really tiny. Drug delivery systems again. Again, we have that micro pump, but this is what it looks like. And now they got prettier ones. This is one of the first generation ones. So you have a sensing system here, I think, or maybe this is the sensor. Let's see. It used to be labeled. Yeah, okay, so the external pump is this thing and the computer. And then you have this tube that delivers the insulin, or the insulin. And then the glucose sensor is over here. Okay, and then you have a radio frequency device that talks to the pump. So it's kind of replacing your pancreas, right? You got nanopore coatings on stents. Okay, and so these coatings help keep the stent from getting all clogged up and whatnot. So, and that's on the end of a catheter. So you put the stent in, and then you use a balloon to expand it into a nice rigid tube. And then you take the balloon and you compress it again, and you pull out the catheter, and the stent stays behind. This is another one of my favorites here, the liposome vesicle. It's been around for a long time. They've been doing research on it, and now they're actually using it for an mRNA delivery system. So, you know, finally these nanoparticles are used for something major like ending our pandemic. Okay, so the below there is the mRNA inside of a biolipid vesicle. That's why you have to keep them cold and stuff, so that this lipid layer doesn't fall apart. And then once it gets in your body, then it starts to fall apart, and then the mRNA gets released. And you guys probably know better on how all that works. I'm not a biotech guy. This is another one of my favorites. It's the pill cam. So you swallow it, and it takes 2 pictures a second as it goes through your body. You wear a little gadget on the outside that collects the pictures through radio frequency transmission through the antenna. And then, you know, you poop out the cam. You don't have to save it. It's a cheap device. It's probably like $30. So I'm sure I wouldn't want to take a pill cam that someone else used. So, you know, it's a good way of inspecting your whole GI tract, all the way from, you know, from your mouth, your esophagus, your stomach, your small and large intestines, and your colon, and all of that. It just keeps taking pictures every 2 every second. And then the doctor gets the recording and then watches it on the computer and looks for lesions and things like that. And he can stop it, rewind it, you know, zoom in if he needs to, and that kind of thing. So that's pretty cool. And there's a close-up of it. Okay, so yeah, we talked about that. The cochlear implant's another kind of cool thing. You might know people, you might have one. This is basically how it works. You have a receiver and a transmitter, and then you put the implant inside. It's an electrode array that goes inside the cochlear canal. Remember, if you have messed up hearing, something's broken in there. So you replace it with an electrode array. And then now you convert the signals from the receiver into an electrical signal, and then your nerves pick up that signal, and then your brain starts to learn how to process it, so it creates sound in your head. Okay. We mentioned pacemakers, lab on a chip. They use these things on the space station to track the health of the astronauts because it's small, light, reusable. You can look at biomarkers for diagnostics. So this is done with DNA kind of stuff. Micro-optics, another one of my favorites. You see a cell phone exploded view of a cell phone camera. So you can see the sensor at the bottom here, and then all the different other components that make up a cell phone camera. And they're like $8. They've gotten so cheap, and that just blows my mind. This is my favorite on the right is a digital mirror device from Texas Instruments. I used to work at TI, and they started developing this in the 80s, and in the 90s they actually got working parts, and now you find them everywhere. So they're in projection systems. Here's a simple one that you might have in your classroom that uses a color wheel. So the color wheel spins really fast. You go red, green, blue, and then you flip the pixel when you want a red one or a blue one or a green one. You flip the pixel one at a time. So each one of those squares here that looks like Cheez-Its, right? They're about anywhere from 7 to 20 microns, depending on which device you're using, and they can tilt by 12 degrees, 30,000 times a second they can tilt. So you know, if you turn it on more often than not, then it's brighter. If you turn it on less often in a second, it's dimmer. So you can adjust the intensity of the pixel, and then depending on what light hits the mirror at any given time determines the color, and you can mix the colors up. So you can get like weird shades of purple. The ones in the movie theaters can do 16 trillion different colors. And then yesterday I was looking around trying to see, oh, well, what's out there now, right? Well, they're pico projectors. So these two companies here are making and there are more companies. They're using this technology to make very small projectors that you can carry around in your pocket. The one on the left is like a little handheld projector, but you can also get it integrated with a phone. And what's interesting is Texas Instruments received an Academy Award, an Oscar, for their technology, for their DMD technology, because what resulted was a complete shift from film to digital. So that was called a disruptive technology. There are very few movie theaters that use film anymore. Some of the OmniMax still use that 70 millimeter film format, but all of the movie theaters that you go to use these chips. And there's some great videos on that. I'm almost done. I hope we can go over a little bit, that you guys don't have to skedaddle. So this is why we care. Okay, so yeah, there are all these cool gadgets and stuff, but we really care because we want students to get jobs, and they have to learn stuff to get those jobs. So this is a quote from Allied Market Research. This is a very recent publication. They said back in 2018, the MEMS market, the Microelectromechanical Systems market, was about 50 billion, and that's just the gadgets. That's not what they go into, right? So remember, some of those things are like 10 cents, 1 cent, 3 cents. Okay, so you can imagine the numbers of these devices that add up to 48 billion. So it was 48 billion in 2018. By 2026, they think it's going to be 122 billion, right? Which translates to a compound annual growth rate of 11%. So that's how much the growth is every year, but that's in terms of money, right? At the same time, these parts are getting cheaper. So we're making more and more and more of them as they're getting cheaper and cheaper and cheaper. And it's still growing at 11% in terms of revenue. Well, revenue means jobs. So the two are related. So here's another graphic. Each color represents a different area in MEMS. Okay, so you've got, SAW stands for surface acoustic wave, optical sensors, fingerprints, of course, are big now, gas sensors, magnetic sensors, and then you got the CMOS imaging systems, and then general MEMS devices, right? Here's another way to look at it. On the left side of the y-axis is the compounded annual growth rate for the given bubble, and each bubble is a different area. So radio frequency MEMS, which is what's in your phones, right, is growing at 30 to 40% compounded annual growth rate every year. And the size of the bubble tells you what the revenue is. So how much money it is, right? So the bigger the bubble, the more money in that area. And then the higher up it is, the faster that area is growing, okay? But everything's growing, and it averages about 11%, which is, down here. So half of the stuff is below, and the other half is above, and you have to weight it with the area of the circle. And this is a graphic showing, yeah, the accelerometers are getting cheaper every year, right? You got year here, price per part on the left. They're getting much cheaper every year, but we're making millions and millions more every year. So the revenue keeps going up. Okay, sensing systems, same kind of thing, right? Imaging is big because they keep putting more and more cameras on your phone, right? To do all kinds of things. You got 3D systems now on your phone. You can take 3D photographs, well, because you got multiple cameras, okay? And all the other sensors. And the other thing that's driving it is the Internet of everything. Everything's connected to the internet, okay? So that's pretty cool. And then this is an interesting one I just found the other day. This is future soldier technology. So soldiers are getting more and more integrated with sensing systems. We remember back in the Vietnam age, they had the infrared things so they could find people at night, and they look kind of greenish, right? Starlight, amplification systems, stuff like that. But now they have all sorts of sensors. They actually have sensors that they wear so that the medical teams know if they're stressed out. If they're too stressed out, they can pull them off of the front line. If there's an explosion and there's 15 soldiers lying around, the medic can tell which ones to go work on first, right? They have algorithms and stuff. They look at blood pressure, temperature, and all that. Because some aren't worth saving. If you're trying to save someone and 3 other people die that you could have saved, so now they have these sensing systems to help those decision-making processes. Of course, batteries are a big deal because you got to run all these things. RF tactical means communication systems, right? So we got all of that kind of thing with the soldiers. Sensor market for automotive, again, growing at 21% compounded annual growth rate, right? And that's between now and 2025. Huge there. And that's because you have autonomously driven cars, right? So on the left is fully autonomously driven. We don't know when that'll happen, but people like Google are working on it. And what that means, fully autonomous, means you don't have your feet aren't being used, your hands aren't being used, your eyes aren't being used, and your brain isn't being used. So you can sleep in the car and it'll take you from point A to B. On the right is somewhat autonomous. So, if something gets close, it'll put on the brakes for you, that kind of thing. And it'll keep you in your lane pretty much. But you still have to kind of pay attention when you're driving a Tesla, right? But they're working on it. So we're just about done, right? Jobs follow compounded annual growth rate. That's why I showed all of those things. And there's something interesting in there for you, for sure. Okay, and so your future's so bright, you got to wear shades. That's an old song. I think it even predates Dr. Ashcroft, maybe not. I'm 59, so this was popular when I was a kid. But anyway, Google it. My future's so bright, gotta wear shades. It's a decent song. Oops. So if you do come to our clean room in the summer, there's a snapshot of a group of teachers we had a couple summers ago before COVID, and they had a lot of fun. Dr. Ashcroft actually came out last year or the year before, and brought a bunch of your students out there. So the new URE experience was, which stands for Undergraduate Research Education, and grant I got is specifically for students, and Dr. Ashcroft submitted or is submitting an additional grant for that. So he'll have more money, and I invite the students to come with their teachers. I have money for teachers too. And then before you come, we want you to take some online short courses so you can kind of understand the processes a little bit, understand the safety protocols and all that. And then when you come, you don't sit in the classroom and listen to me lecture. You actually get to go in the clean room, start doing stuff right away. Okay. And then there's more about this specific project that I talked about a few weeks ago, and it's posted on the Nano Hub site. It might also be posted through the Mintech site. So that's it. So I'm going to stop sharing. Well, not go to gallery view maybe. You guys can look at this stuff. We got 16 people left. So anyway, we got the Minty-Sig group. Most of you know about that. The students are welcome to join. My email is mpleil@unm.edu. And you can always call me if you want to chat, or we can set up a Zoom time, and I'm hoping to visit your class more often in the future. So I went a little over time. I hope that's okay. You can unmute and ask questions, and nobody put a question in the chat box, so.
I think they were just all shocked.
I probably went too fast.
Oh no, that's way slower than I go usually. I'm way faster than that. Anyone have any questions?
Please ask questions.